Okay, moving on to question 5. Again, PF5, the next example after COCl2. So we repeat the same process. We determine what's the central atom first. In this case, phosphorus is the central atom because phosphorus is the first element in the molecular formula. Alright, and then it's also the least electronegative. So next, we look at the number of valence electrons contributed by phosphorus and fluorine. Phosphorus, group 15, 5 valence electrons. Fluorine, group 17, 7 valence electrons each. So you can imagine I'll draw a central p atom surrounding by 5 fluorine atoms. Okay? So in this case, we know that fluorine, being group 17, will need 1 valence electrons to achieve octet. So we all form a single bond first. So you can see I form one single bond with fluorine, the first one. A second single bond with another fluorine. And then the third one, I form another single bond with fluorine to achieve octet. The next one, another single bond to achieve octet for the other fluorine. And last but not least, the last one. Okay, while drawing in all the other electrons for fluorine. So each fluorine will have 7. Okay, and then you can count the number of valence electrons by phosphorus. 1 cross, 2 cross, 3 cross, 4 cross, 5 cross. So in total there are 5 valence electrons contributed by phosphorus. Check. Each fluorine has 7. Fluorine has all achieved octet. Okay, so it's now left with the phosphorus. So you look at phosphorus. Phosphorus is a group period 3, right? So can you expand octet structure? Yes, it can. So take a look. 1 pair, 2 pairs, 3 pairs, 4 pairs, 5 pairs. You have 10 electrons. Because phosphorus is in period 3, you can expand its octet structure because of energetically accessible and vacant d orbitals. So it's perfectly fine for it to expand octet. So now we need to count the number of bond pairs now. 1 bond pair, 2 bond pair, 3 bond pair, 4 bond pair, 5 bond pairs. You have no lone pairs. So 5 bond pairs, 0 lone pairs around the central p atom. The shape will therefore, based on your VSEPR theory, will be trigonal bipyramidal. So you can see what's a trigonal bipyramidal. You will see later on triangular base with 2 pyramids. You have 2 bond angles, 90 degrees on the perpendicular axis and 120 degrees on the plane. Okay, so to show this, let's take a look. This will be an easier way to take a look at it. Okay, so you have PF5. Okay, you have a triangular base, then with the 2 apex forming 2 pyramids. Alright, so you can see I have a bottom pyramid. I also have a pyramid that's on top. Okay, so this is how you show trigonal bipyramidal. This is one way. Okay, you can make use of dotted lines like this to show the 3-dimensional plane. Alternatively, like what we went through in lecture notes, you can also show using dash and wedge. So what's a dash and wedge? The dash and the wedge to show 3-dimensional. So again, the wedge represents the F fluorine bond is pointing out of the plane, whereas the dash here shows that the fluorine is pointing into the plane. Alright? Okay? So in this case, to determine the polarity, we know that fluorine is more electronegative than phosphorus. Okay, so you can put delta minus on all the fluorine. We have a delta plus on the phosphorus. So the dipole moments will all point towards the fluorine atoms. So you can see me indicating all the dipole moments in reds along the bonds. Okay? Now let's take a look at whether it resolves each other. So from lecture notes, we know that trigonal bipyramidal can resolve each other. Why? So these two here, I'm circling in red, can cancel each other out because it's directly opposite each other. Whereas these 3 that I'm highlighting in green now can cancel each other out just like a trigonal planar. Okay, so as a result, there is no dipole moment, or rather no net dipole moment. And therefore, it is going to be non-polar. Okay, with that, we're going to move on to SPF 6- and SO42- in the next video.